Alrighty, hello everybody, and welcome to the first video for heat transfer for the semester. So this is just going to be, this first week we covered 2 lectures worth, so it's going to be chapter 1 and chapter 2. And basically what we're going to be going over is just heat transfer itself, all the methods of heat transfer, and the general heat equation. So for heat transfer, heat itself is a form of energy, and heat transfer occurs when there's a change in temperature. So when it comes to the heat that transfers, it usually goes from a high temperature and it wants to go towards a low temperature. You can kind of think of it as when you're opening an oven, all that hot air wants to escape into the lower temperature and diffuse and just kind of, because it's similar to I think it's the second law of thermodynamics, which states that you want temperature equilibrium. So everything wants to diffuse, so it ends up being the same. So the amount of heat transfer like that happens in an object itself really depends on its internal properties and how well it's going to be able to it has to do with like the density and a couple other factors and how well it's able to push through and instead of just kind of dying and not going that far into the actual object. So before we get into the basic modes of heat transfer, one important thing to talk about is steady state and what a steady state is. So most of the things we're going to be talking about this semester are going to be steady state. And so a steady state is when a property like temperature, which is what we're going to be dealing with most of the time, occurs and stays consistent independently of time. So it's not like it's not going to decrease over time. We're just going to assume that in the steady state, it's just going to be the same over time. So now we're getting into the methods or modes of heat transfer. And the first one we're going to look at, it's kind of side by side. That's just how I did my notes. But we're going to look at the left side first. We're going to talk about conduction. So conduction is heat transfer that occurs in a solid or a stationary fluid. So it turns out that a solid or a stationary fluid kind of act very similar to each other. And so when we look at conduction, we're going to look at the Fourier's law of heat conduction. And so this law states that the heat that exits any body is proportional, which is what the alpha means, to the area, and it is also proportional to the change in temperature and inversely proportional to the thickness of said object. So if we take out that proportionality, we can add in another term, which is a proportionality constant, and which gives us the final value, which is Q is equal to negative K, which a negative K is the thermal conductivity. So basically it's for each independent, because as I said earlier, every object, let me just scroll up to see it. So the amount of heat transfer depends on the internal properties. So K, which we will look at, I know I've written it down somewhere, so we'll find it eventually. So K takes into account those internal properties. And then we also have the area. So just the dimensions of whatever solid or liquid it's diffusing into times the change in temperature over the thickness. And also for sign convention, K is always represented as a negative. And so when you simplify this equation down, you have Q. Oh, also sometimes you're looking at the heat flux, and when you're looking at the heat flux, that unit is described with, I believe it's joules would be the right unit, over meters squared. So it's similar to like in thermodynamics when something is, can't remember the exact term for it, but it's divided by the mass. So in this case, it's going to be divided by meters squared, which is why we lose that area term right there. And that's going to be, yeah, so that's our 1.2 equation. I numbered these two. I don't think I'm going to be numbering the rest, but anyways. So that's just a brief overview of conduction. This is like for the next 4 weeks we're going to be covering conduction, and then we're going to go to convection And then we're going to move to radiation like the last 2 weeks. So this is just very brief overview. So convection is the heat transfer that occurs between a surface and a moving fluid. So you can think of it as like a lake. When you're out over on a lake and you have, we'll consider the liquid, even though it is a liquid, we'll consider that water to be a surface. And then how the wind takes some of that heat off of the water surface and brings it into the air, and just different types of examples like that. And so there are different types of convection. You could have natural, which is like similar to what I just explained, what happens between like a river and just air that blows through. And then you have forced. So forced is making that fluid pass over the surface to increase heat exchange. So you can think about how, like in a convection oven, it uses a fan so that when you have that element, which is the heat source basically. So it creates that heat, and that fan forces air to push over top of that element so that the heat gets pulled off and it gets pushed around in the environment and kind of creates that convection. It's not great to explain convection with calling it convection, but the air circulates with it. And again, naturally, so when there's a large change in temperature in the surrounding. Okay, so yeah, this is how it kind of happens in natural. So like if there's a large change in temperature, so if you have a higher temperature, it means there's going to be a lower density, and that means there's going to be a natural air circulation that's kind of close to that object itself. And so when we look at convection, the law that comes to mind is Newton's law of cooling, and it's the famous differential equations coffee cup experiment. And so the heat from convection is proportional to the surface area, which is slightly different than just the conduction, because it's the surface area of, well, that top surface, right? And it's multiplied by the change in temperature. So it's going to be the surface temperature minus the temperature of the surrounding, which for this class, I don't know how I feel about it, how I like it that much. It's T infinity. I would say T surrounding. So it's like the surface temperature and then the surrounding air temperature. And so to get rid of that proportionality again, we'll bring in another proportionality constant, and this itself is going to be the convective, I have wonderful writing, convective heat transfer coefficient. So that's pretty much it. And so these two, both convection and conduction, have a linear temperature difference. As we get into radiation, we're going to see that's not the case for that. So radiation is energy that's transferred by electromagnetic waves, or also known as photons. And so when we look at radiation, we're going to see Stefan Boltzmann's law, which says that the heat from radiation, actually we'll start up with the proportionality. So the heat of radiation is proportional to the area times temperature to the fourth power. So this is massively different than the past two, which just have linear linear temperature difference. There we go. So the thing that needs to be stated when it comes to, actually no, I'll explain. Okay, so first we'll get rid of the proportionality, and then we bring in sigma, which is yet another proportionality constant, and this proportionality constant is going to be 5.67 times 10 to the negative 8 watts per meter squared times Kelvin to the fourth. And it's very important that you do not forget that temperature is going to be in Kelvin only. And if you don't have it in Kelvin, you're going to be in a world of hurt. But to be honest, when you're looking at Boltzmann's law, you're going to see K in there anyways. And as you should, it's good practice to, whenever you're writing out the equations and you're subbing in numbers for this equation, you want to write down the units anyways. So even if you make like a slight mistake and you don't do Kelvin right away, once you write down Boltzmann's constant, you're going to see that K4 on the bottom, and you're like, oh, okay, I made a slight mistake. Let's go back and fix that. And so due to both the very small number when it comes to Boltzmann is constant and the Cordic power on the temperature. So if you have a low temperature, radiation is going to be an absolutely tiny amount when it comes to how much it's producing. And when you have temperature which is very high, since you're going to have any number to the power of 4, it's going to be astronomical. It's going to be really dominant within whatever the situation is, whatever the topic you're evaluating is. And so basically, since this is actually the change in temperature, this is just written in another way: sigma times the surface area. No, not surface area. This is just the regular area times the surface temperature minus the surrounding temperature, both to the 4. And so to the right here, we have basically what I was talking about, heat flux. And so it's heat transfer per meter squared, which is perpendicular to the direction of heat transfer. And so these equations do not include the area. And then we represent this by Q dot. That dot should be kind of on top, or Q double prime. And as I said earlier, I promised we'd come back to the thermal conductivity. Here it is. So the thermal conductivity has to do, so again, the internal properties, right? And so it has to do partially with the electronic portion. So how the electrons are oriented, as well as the lattice portion, which has to do with like the density and how the atoms are arranged, and how the lattice, because the lattice in essence defines the properties of the object itself. So that's chapter 1. That's pretty much the base overview of all of these things. And now we're going to get into chapter 2, which is just simply the heat equation. So now we're just focusing on conduction now. So when we're looking at conduction, the objective is to determine the temperature field in a medium. So a medium is just any object that's made of like some material or specific type of matter. And so what is the temperature field as a result of the conditions that are acting on it? So now we look at this wonderful elemental, what's the best way to call it? I can't remember exactly, but it's basically you look at it in all the directions. So here it is. This is going to be and this is also to do with Cartesian space, because later on we're going to be looking at radial, so going down a pipe, and heat transfer that occurs in a sphere. So here we have in our Cartesian lovely little cube what's going on. Okay, so when we look at the cube, so the parameters, so the height, the width, and the length are all going to be defined by dx, dy, and dz. So these are the parameters. If you multiply them all together, that's how you're going to get the volume, right? And so when we're looking at what goes in and what goes out, so we have these qx value, qx, qy, and qz. Those are all the values that go in for the energy balance. I didn't mention this before, but you can probably see this is how the energy balance works. So, and then the heat values that come out are going to be qz plus dz, and then qy plus dy, qx plus dx. We'll go on to explain what exactly. So that just kind of represents what leaves the element. That's just how it's the notation is. And so we also have in the middle is going to be energy that's stored. So this is the energy that goes in but doesn't leave. So the stored energy is going to be calculated by the mass times the specific heat times the change in temperature over the change in time. These are both partial derivatives, by the way. And so this can also be written as, because mass is density times volume. So we have the density times Cp in the partial to temperature over the thickness to, I might have made a mistake. I think that might need to be the thickness. I'll double check on that, actually. I'll put a note over top if it is. So when we split off density and volume, this is just dx, dy, dz. That's how you find the volume. So that's all the energy that stays in. So the energy that's generated from it's not heat that goes in, it's heat that kind of started, or energy that started in that medium, which then goes out. That's the Q times the volume. So basically, we'll see how well I do this, but this is going to be the rough calculation breakdown of how the entire energy balance works out, right? So, excuse me. Okay. Okay, I'm good. Here we go. So for the calculation, each exiting value is differentiated using Taylor series. So this is what we get after putting that through the Taylor series approximation. And so you get qx plus dx equals qx plus dx to the partial derivative of qx over the partial derivative of the change in thickness. And so this goes the same for both y and z. And so now we're looking at what's going in, what's coming out. And so this is kind of a range, even though E out, you can put it on that side, you can tell it's negative. So we're kind of going to be, the way this is kind of arranged is so that we can find the stored energy. So the E in values, as I said earlier, it's going to be Qx, Qy, and Qz. And then the generated values, again, like I said earlier, it's going to be Q dot times the volume. So all those parameters multiplied together. Then energy out is going to be minus Qx plus dx, Qy plus dy, Qz plus dz, and those are all subtracted. Just like I said before, EST, stored energy, is going to be represented by that. And so there's a bit of, if you can see to the bottom, there's a lot of simplifications that happen. And so each heat rate, so Qx, Qy, and Qz, you find these using Fourier's law, like we said earlier. So each of these are broken down into negative k plus dy times negative k times, dy times dz. So these are all going to be the areas. It's basically the area. And so di t over di time, basically, like we said before, Fourier's law. And so a key thing to take into account, which we are, okay, that's actually a bit of a later thing. We'll come back to thermal diffusivity. So what we do now is taking these Qx, Qy, and Qz, we sub them into the equation so that, where was the part that I got lost at? Oh, I completely skipped a step that I wasn't sure exactly how. Okay, so as you can see, we lose the green Q out for a little bit because I'm kind of a little bit confused as to how it goes from this all the way down to the general heat equation at the end. So I may just save off on posting half of this video and I'll come back and explain it later. But if not, if you're seeing this, I've carried on anyways, and I will probably further explain in the future. So as we skip the step that kind of had me slightly confused, because I'd much rather skip over it entirely than say something that's wrong. So we skipped that part, and so what we end up getting when we put these values into the equation is all of this. So we have, I'm just going to say it for each respective part. So there's Qx. So the Fourier's equation is subbed into there. I think I might see what it is now. So these parts here, I believe, come from, yeah, okay, that's what it is. So the change over the change in thickness times dx, I believe that's how it's rearranged from the E out. So I think these parts are going to be the D out, the Q out, then that's Q in. So you have the partial derivative over I can't see there it is. Partial derivative over the change in thickness. minus K times the area times the change in temperature over the change in thickness times dx. And that's going to be repeated for both Y and Z. And then you have the generated heat, and then you have the stored heat. And so these two just don't change at all. These two are kind of homologated together and put together. Yeah. So, and now, as you can see, there's a whole bunch of red lines on both sides. So what we can do, since we have dx, dy, and dz on both sides, we can just divide them all out. So that's going to make our much nicer. Oh, also, don't want to miss this. We also divide by k. So k is in each one of those. So we divide by k, which ends up giving us q over k. So to give us the final heat equation, we have the partial derivative, the second partial derivative of temperature over dx squared, d squared t over dy squared plus d squared t over dz squared plus q dot over k equals to 1 over alpha over dt over dt, top T being temperature, bottom T being time, which is where we come back up to what is alpha. Alpha is thermal diffusivity. So it's the rate of the temperature spread through a material. So it has to do with the thermal conductivity, and it's divided by rho times the specific heat, which, when you put those two values together, is going to be how much energy can be stored. So when you're looking at what values contribute to different values of thermal diffusivity, if you have a high thermal conductivity and a low value of how much energy can be stored, so it's kind of intuitive. So if you have a lot of conductivity and you can't store a lot of energy, it's going to spread very quickly. It's kind of that resistance. But if you instead have not very strong thermal conductivity and a high storage of energy, it's not going to pass very well, because that energy is going to want to stay within the actual medium. And so when we take this and, okay, just want to make sure that we're clear on where everything comes from. Okay, so we have, this is both a Q in and a Q out value for X, Y, and Z. And then we have the stored, which comes from that Q. And then we have this here. And so where the alpha comes from, in essence, I'm going to get out my white marker here. So since we have rho, oh goodness, that looks bad, Cp over K, because we divided both sides by K, that in essence is going to be alpha inverse, because alpha is equal to K over rho Cp, which is why we end up getting that inverse alpha value. So that's where everything comes from. And so if we're going to simplify it even further, you can do the nabla, which is just nabla squared T, and that represents the whole gradient. And so plus K, Q over K equals 0. And so when we have equals to 0, that's when there is no stored energy. One second. Yeah, so there's no stored energy that we deal with. And when there's no heat generated, there's going to be, you lose that K over Q over K value. I'm going to mess that up a lot, so forgive me. And so when we do a lot of the work on these examples, like what we're going to be tested on throughout the course are pretty much just going to be 1D. And my teacher, I'm not going to say that out loud, it's probably smart if I don't, has basically said he will show us how to attempt two-dimensional problems, but he won't expect us to know how to do it. So there it is. That was a slightly messier introduction, as I kind of got lost, but if anything, it helps that I kind of was able to find my way through. But the most important things as we go over it again are What is heat transfer? So heat transfer is a form of energy. Conduction is heat when it transfers through a solid. Convection is heat transfer that happens between a surface and a moving fluid. Radiation, energy transferred by electromagnetic waves. And the second thing, which is going to be one of the fundamental bases of conduction, at least, is going to be the general heat equation. So how the heat equation is going to depend on the gradient of temperature in all directions, and plus the heat generated divided by the thermal conductivity, which is equal to the inverse of the thermal diffusivity and the change in temperature over time. So that's it for the first week of heat transfer. I will see you guys next week.